Hey, Trig. We are starting, this is Unit 3-4, the last unit in Chapter 3, or the last chapter in Unit 3, something like that. Okay, distance equals rate times time, something we're familiar with, correct? If you were to solve that for rate, in other words, have rate equals, you would just divide by time, right? Distance divided by time equals rate. All right, if I went 100 miles and I made it in 2 hours, I was like, oh, I wonder how fast I was going. I take 100 miles divided by 2 hours. I was going 50 miles per hour. All right, we know that. It's very, very similar with angular speed and linear speed. Okay, as I'm opening my angle, all right here, as we're opening theta, okay, the speed is theta divided by time, just like our rate in the last slide was distance over time, okay? Omega is what we use for the Greek letter omega, is what they use for angular speed. That's how fast is this little guy opening, okay, this angle. Now, the point P, the linear, we call that the linear speed, and we use V kind of like for velocity. We take this, oh gracious, yeah, this arc length divided by time, okay? So thinking back that we're off the unit circle now, okay? So we might have a radius of 5 or something. Remembering that S is R times theta, correct? S is R times theta. Then another way to think of this is R times theta over T. Oh, and we just saw that theta over time is omega. So I could think of my linear speed as the radius times the angular speed. You know what I like to think of for this? Because some people get confused. They're like, well, aren't they opening at the same? Wouldn't they be the same? Omega and velocity, angular speed and linear speed, wouldn't they be the same? Were you ever on a merry-go-round and you're real close to the center and somebody else is way out way out at the edge, and that person's like, I can barely hold on, and you're like, this is not going that fast. Okay, that's how I like to relate it. The speed that you're going out at the edge here is different than the angular speed, like right here. How fast is the angle opening compared to how fast is this point going? Okay, so let's just try to get those settled in your head. Omega is the angle in radians. Notice theta is in radians again, not 20 degrees over time, okay? In radians. This whole time now we're in, all these formulas only work with the mathematical measurement of the angle, which is radians, not the degrees anymore. So here we go. Here's a linear and angular speed. Okay, consider the following. The human joint that can be flexed the fastest is the wrist. It can rotate through 90 degrees or pi over 2 radians in 0.045 seconds while holding a tennis racket. The angular speed of a human wrist swinging a tennis racket, therefore, is, okay, think back to our definition. If we want to know the angular speed of a human wrist swinging this tennis racket, okay, remember what it was? Look at your notes. Okay, theta over t. We have everything we need. I'm not going to take 90 degrees over t. I'm going to take pi over 2 over the time it takes to swipe that tennis racket from up here to down there in 90 degrees. Okay, so about 35 radians per second. If you do that on your calculator, pi divided by 2 divided by 0.045 is about 35 radians per second. That's the angular speed. Okay. All right, let's try this. Suppose some point P is on a circle. Its radius 10 centimeters. And ray OP is rotating with an angular speed. This time we know the angular speed. We know omega. Okay. It's pi over 18 radian per second. Find the angle generated by P in 6 seconds. Okay, so what is theta? Okay, before we knew theta was pi over 2 in the last problem. Now we know omega, we're trying to find theta. And then we'd like to know the distance traveled by P along the circle. You have to realize then that that's S, that's arc length. When they ask for these things, they're asking for the angle, that's theta. They're asking for the distance traveled along the circle, that's S. Okay, and then linear speed was the velocity that we saw. Okay, so of course to find theta here, I know that omega is theta over t. I would usually just stick the numbers in right there. They solve for theta by multiplying by t first. So they're taking the angular speed times 6, pi over 18 times 6, you get pi over 3 radians. So about 6, well, not about, exactly 60 degrees, okay, or pi over 3 radians. The distance traveled, okay, if we want to know what S is r theta, correct? We're not on a unit circle anymore. We're at the radius is 10. So for letter B, I'm going to have to take r times theta. So 10 times the theta we just found, pi over 3. 10 pi over 3, I usually would figure out what that is. I don't know, how many centimeters is that? That doesn't make sense to me. 10 times pi divided by 3, about 10.5 centimeters, okay? 10.5 centimeters, that makes sense to me. If the radius is 10 and I'm going up 60 degrees, you know, that length seems like that would be a little bit more than 10. 10.5 sounds about right. The linear speed, we had several formulas for linear speed, right? So they decided to use the r theta since we have the r omega, since we have the angular speed from the beginning. Okay, let me show you again. When I say linear speed, we had these, look in your notes, we had these three. We either take the arc length divided by time. We could do that. We could take r times theta divided by time, which is, you know, we already have omega, so we might as well just take the radius times omega because we have more exact things for that. You know, we have the exact, they told us omega. They told us the radius. Might as well find the linear speed is 5 pi over 9 centimeters per second. Okay, and again, I might take 5 pi divided by 9. That's 1.75 about. Okay, 1 3/4 centimeters per second. Just to give you a little, you know, to say 5 pi over 9 centimeters per second doesn't tell me as much as 1 3/4 centimeters per second. I can picture that a little better. Okay, so let's try this one. A belt runs a pulley of radius 6 centimeters at 80 revolutions per minute. And there's the figure. Find the angular speed of the pulley in radians per second. Find the linear speed of the belt in centimeters per second. Okay? I want you to see that they've already told you. They've already told you the angular speed, but they've given it to you in revolutions per minute, and they want it in radians per second. So we're not really using a formula that we learned for letter A. Okay? For letter A, we're going to take the 80 revolutions per minute and change that to 80 revolutions in 1 minute is the same as 2 pi radians, and 1 revolution is 2 pi radians, and 1 minute is 60 seconds. It's just that whole, we've done this, okay? We're changing revolutions to per minute to radians per second because they asked for that, okay? So when you divide that out, you get 160 pi over 60. The angular speed, omega, is 8 pi over 3 radians per second. I just want to make sure you realize that you had the angular speed from the beginning, just not in the right units. Okay, let's look back at the way they said it. A belt runs a pulley of radius 6 at 80 revolutions per minute. 80 revolutions per minute is the angular speed, but they wanted the angular speed in radians per second. Okay. So I just wanted you to see that you're just really, that was just some unit switching. The linear speed, again, I'm going to use my r times omega, my radius times my angular speed. And so I get 6 times 8 pi over 3, 16 pi, and they changed it there for me, which I'm glad, 50 centimeters per second. Okay, these are nice applications of radian measure. Okay? All right, good luck. I'll see you in class.